You know, there's something we tell people all the time about the universe, something that shows up in documentaries and textbooks and popular science articles, something that's repeated so often it's become conventional wisdom, accepted without question. And that statement is, the universe is infinite. It goes on forever in all directions. There's no edge, no boundary, no end, just stars and galaxies and space stretching out to infinity. And I'm here to tell you that this might be completely wrong. In fact, the evidence suggests it probably is wrong. The universe is almost certainly not infinite. It has a finite size, a boundary beyond which nothing exists, an edge to space itself. And what's even more remarkable is that we can potentially measure this, we can determine the size of the universe, we can find where it ends. We've been lied to, or at least misled, about one of the most fundamental facts about reality. And today I'm going to show you why the universe is finite, how we know this, what it means for the edge to exist, and what happens when you reach the boundary of all that is. Now, before we dive into the evidence, I need to explain why this misconception is so widespread. Because it's not that scientists have been deliberately deceiving people, it's that there's a subtle distinction that gets lost in translation from technical scientific discussion to popular presentation, a distinction between what we can observe and what actually exists between the observable universe and the universe itself. When scientists say the universe might be infinite, they're often talking about a specific technical question about the geometry of space, about whether space is flat or curved, about whether if you traveled far enough in one direction you'd eventually come back to where you started, like traveling around the surface of a sphere, or whether you could keep going forever in a straight line. And the best measurements we have suggest that space is very close to flat, maybe exactly flat, and flat space in the context of general relativity typically means infinite space extending forever in all directions. But here's what gets lost. Those measurements only tell us about the observable universe, the region of space from which light has had time to reach us since the Big Bang. And that region is finite. It's about 93 billion light years in diameter. And we have no direct information about what lies beyond that horizon, whether space continues forever or whether it ends. And there are very good reasons, both theoretical and observational, to think it ends, to think the universe is finite, much larger than the observable region, but still finite, with an actual edge beyond which nothing exists. So let me walk you through the arguments carefully, starting with the most fundamental and working toward the observational evidence that's accumulated over the past few decades. The first argument comes from the Big Bang itself and the nature of cosmic expansion. We know the universe began in a hot, dense state about 13.8 billion years ago and has been expanding ever since. Space itself is expanding, carrying galaxies along with it, and this expansion is described by Einstein's equations of general relativity combined with observations of how fast galaxies are moving away from us. Now, here's the key question. When the Big Bang happened, did it create an infinite amount of space or a finite amount of space? If it created infinite space, then the universe has always been infinite. It started infinite and remains infinite even as it expands, which seems conceptually strange because you're expanding something that's already infinite, but mathematically it's coherent. An infinite space can expand by having every point move away from every other point while remaining infinite. But if the Big Bang created a finite amount of space, then the universe started finite and remains finite as it expands. It's just getting bigger. The finite volume is increasing. But it's always finite at any given time, and this seems more natural, more in keeping with the idea of the universe having a beginning, starting from a definite initial state and growing from there. And most cosmologists, when pressed, will tell you they think the universe is finite that the Big Bang created a finite region of space that's been expanding ever since, because the alternative, that the Big Bang somehow created an infinite amount of space instantaneously at time zero, seems to require an actual infinity to exist physically rather than just mathematically, and actual infinities are problematic. They lead to paradoxes and conceptual difficulties that make physicists uncomfortable. Moreover, if the universe is infinite, then an infinite amount of matter and energy was created at the Big Bang, which seems to violate conservation principles, or at least to require extraordinary fine-tuning of initial conditions across infinite space, whereas if the universe is finite, we're talking about a large but finite amount of matter and energy, which is conceptually simpler and doesn't require coordinating initial conditions across infinity. So the theoretical preference, based on simplicity and avoiding infinities and making sense of the Big Bang as a genuine beginning, is for a finite universe. But that's just theoretical preference. What about actual evidence? Well, the key evidence comes from measurements of the cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe that's been traveling to us for over 13 billion years. The CMB has been measured with extraordinary precision by satellites like WMAP and Planck, and these measurements tell us about the geometry and composition and history of the universe with remarkable accuracy. And one of the things they tell us is the curvature of space, whether space is positively curved like a sphere, negatively curved like a saddle, or flat like an infinite plane. The measurements show that space is very close to flat. The curvature is consistent with zero within measurement uncertainties, which initially suggests infinite space, because flat space in general relativity typically extends to infinity. But here's the crucial detail that gets overlooked. Flat space can be finite if it has a specific topology, if it's wrapped around on itself in ways that don't require curvature. Think of the surface of a cylinder. It's flat in the sense that parallel lines remain parallel, and angles and triangles add up to 180 degrees. But it's finite in one direction because it wraps around. If you travel far enough around the circumference, you come back to where you started. Or think of a torus, a donut shape, which is flat but finite in two directions. It wraps around both ways. These are flat geometries with finite volume, and the universe could have a similar topology, flat but wrapped around on itself in three dimensions in ways that are hard to visualize but mathematically well defined. And if the universe has such a topology, then it's finite, even though it's flat, and we wouldn't necessarily detect the curvature because the wrapping could happen at scales larger than the observable universe. The space could wrap around at distances greater than what we can see, so within our observable region, everything looks flat, even though the total space is finite. So flat space doesn't necessarily mean infinite space. It could be flat and finite, and in fact, there are specific predictions we can test. If the universe wraps around on itself, then we should see patterns in the cosmic microwave background. We should see the same structures repeated in different directions because light has traveled all the way around the universe, and we're seeing the same regions from different angles. Researchers have looked for these patterns, searching for matching circles or correlated temperature fluctuations that would indicate wrapping, and they haven't found definitive evidence yet, but the searches are limited by the size of the observable region and the resolution of the data. And the absence of evidence isn't evidence of absence. It just means the wrapping, if it exists, happens at scales larger than we've been able to probe so far. But the possibility remains, and many cosmologists think it's likely, that the universe is finite with a flat wrap topology rather than truly infinite, because finite makes more sense conceptually and doesn't require actual physical infinities. Now let me give you another line of evidence that points toward a finite universe, and this comes from the theory of cosmic inflation. Inflation is the idea that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, doubling in size again and again in an incredibly short time, growing from subatomic scales to potentially cosmic scales in less than a trillionth of a second. Inflation was proposed to explain several puzzling features of the universe, like why space is so flat, why the cosmic microwave background has the same temperature in all directions even though different regions couldn't have been in contact, why we don't see magnetic monopoles and other exotic particles that theories predict should have been created in the Big Bang. And inflation solves all these problems beautifully. It takes a tiny region of space that's uniform and inflates it to cosmic size, smoothing out irregularities and creating the flat, uniform universe we observe. But here's the key point. Inflation operates on a finite region. The inflating patch starts small, maybe just the Planck length, 10 to the minus 35 meters, and expands to enormous size, but it's always finite. It's a specific region of space undergoing this rapid expansion, not an infinite expanse. Now, the inflating region can grow to be much larger than our current observable universe. It could be millions or billions or trillions of times bigger, but it's still finite. It's a bubble of inflating space surrounded by other regions that aren't inflating or are inflating differently. And this picture naturally gives you a finite universe. Our entire observable universe and much more beyond it all came from this one inflating patch, and that patch, while enormous, is finite. So inflation, which is supported by observations and has become the standard model of early universe cosmology, predicts a finite universe, not an infinite one. Moreover, inflation gives us eternal inflation. The idea that once inflation starts, it never completely stops. Some regions stop inflating and become universes like ours, but other regions keep inflating and spawn new universes, and this process continues forever, creating an infinite number of finite bubble universes within an eternally inflating space. So even if the broader inflating space is infinite, each individual universe within it, including ours, is finite. It's one bubble among many, and bubbles by definition have boundaries. They have an inside and an outside, a region where inflation stopped and conditions allow for matter and galaxies, and beyond that, a boundary where the inflating space continues. So the multiverse picture that emerges from inflation has infinite numbers of finite universes, not one infinite universe. And this distinction is important because it means our universe, the space we inhabit, has an edge. Now, you might object, wait, if there are infinite universes in eternal inflation, doesn't that mean the total space is infinite? So in some sense, the universe is infinite after all. And that's technically true. The totality of everything, the full multiverse, might be infinite. But that's not the same as saying our universe is infinite. Our universe is one finite bubble. And when we talk about the universe in cosmology, we typically mean our bubble, the region that came from our Big Bang, the space that contains our galaxies, and that will expand and evolve and eventually die, not the totality of all bubbles. So yes, the multiverse might be infinite, but the universe, meaning our observable universe and everything that came from the same Big Bang, is finite. And that's what I mean when I say we've been lied to about the universe being infinite. The confusion is between the universe and the multiverse, between our bubble and the totality of all bubbles, and most popular presentations don't make this distinction clear. So let me be precise. The universe, meaning the region of space that originated from our Big Bang, that contains all the matter and energy that will ever be causally connected to us, that includes our observable region and everything beyond it, up to the boundary where inflation was still occurring or where our bubble ends, is almost certainly finite, probably enormous, far larger than the 93 billion light-year observable region, but still finite with an actual edge beyond which nothing from our universe exists. Now, what does it mean for space to have an edge? This is where things get conceptually tricky, because we're used to edges being boundaries between something and something else, like the edge of a table separating the table from the air around it, or the edge of the ocean separating water from land. But the edge of the universe isn't a boundary between our space and some other space. It's a boundary between space and nothing, between existence and non-existence, and that's hard to visualize or even think about coherently. When I say there's an edge to space, I mean that space itself terminates, there's a last point, and beyond that point, there's no space, no distance, no locations, no geometry, literally nothing. Not empty space, because empty space is still space. It's still part of the geometric structure of the universe. You can move through it, place objects in it, measure distances across it. But beyond the edge, there's no geometric structure at all. The concepts of distance and location and direction don't apply. Asking what's beyond the edge is like asking what's north of the North Pole. It's a category error. The question doesn't make sense because you've reached the limit of the framework within which the question is formulated. And this is deeply counterintuitive. Our brains aren't wired to understand the end of space. We want to ask what's on the other side, but there is no other side. There's no beyond, because beyond requires space, and there is no space there. The universe doesn't sit in some larger container. It's not embedded in a higher dimensional space that continues past the edge. The edge is absolute, final, the end of everything spatial. Now, you might wonder, if the universe has an edge, can we reach it? Can we travel to the boundary and see what it's like? And the answer is complicated because of cosmic expansion and the speed of light and the size of the universe relative to the observable region. The observable universe, the region from which light has had time to reach us, is finite with a radius of about 46 billion light years, which grows to 93 billion light years in diameter when you account for how much space has expanded while the light was traveling. And this observable region is a sphere centered on us. We're at the center of our own observable universe, just as every observer is at the center of their observable universe, because we can only see regions from which light has had time to reach us. But the actual universe, the full extent of space from our Big Bang, is much larger than the observable region. Estimates vary, but it could be hundreds or thousands or even millions of times larger, depending on how much inflation occurred and how long the inflating phase lasted and what the geometry is. So the edge of the universe is far beyond our observable horizon, far beyond the region we can see with any telescope, no matter how powerful, because light from those distant regions hasn't had time to reach us yet and never will because of accelerating expansion. The expansion of space is speeding up due to dark energy, and this means that distant regions are receding from us faster and faster, and at some distance they're receding faster than light, not because they're moving through space faster than light, which would violate relativity, but because space itself is expanding fast enough that the distance between us and them is increasing faster than light can close the gap. This creates a cosmic horizon, a boundary beyond which we can never receive signals, regions that are forever causally disconnected from us, and this horizon is currently at about 46 billion light years away and will expand somewhat over time, but will always remain finite. And the edge of the universe is beyond this horizon, far beyond, so we can never see it. We can never travel to it, no matter how fast we go or how long we travel, because the expansion of space carries it away from us faster than we can approach it. So in practice, the edge is unreachable, it's forever beyond our causal contact, and we're confined to a finite observable bubble within a larger finite universe whose full extent we can never directly observe or reach. But even though we can't reach the edge, we can infer its existence, we can use cosmological theories and observations to deduce that the universe is finite, that there is an edge out there beyond the horizon, and we can even estimate roughly how far away it is based on models of inflation, and the geometry of space. Different models give different answers, but typical estimates suggest the full universe is at least hundreds of times larger than the observable universe, which would put the edge at distances of tens of billions or even trillions of light years, incomprehensibly far, but still finite. So the edge exists. It's out there somewhere, beyond what we can see, but we'll never reach it or observe it directly. We can only know about it through inference and theory. And this raises fascinating questions about what it would be like to approach the edge if you could somehow get there, what you would see, what would happen as you reach the boundary of all existence. Let me speculate a bit, because while we can't observe the edge directly, we can think through the physics of what must happen there. First, as you approached the edge, you'd notice that there's less and less matter around you. Galaxies would become sparser. The universe would become emptier because you're moving away from the center of the inflated region, where matter density is higher, toward the periphery, where there was less time for structure formation and where the universe is younger in some sense. And eventually, you'd reach regions where no galaxies formed at all, where the density was too low or the expansion too fast for matter to clump, just diffuse gas and radiation, and perhaps not even that, perhaps just empty space approaching the boundary. And then you'd reach the edge itself, the last point in space, and here physics becomes uncertain because we've never encountered such a situation and our theories might break down. One possibility is that space simply terminates, there's a sharp boundary, a last geometric point, and attempting to move beyond it would be impossible, not because there's a wall or barrier, but because there's nowhere to move to. The concept of moving forward becomes meaningless because there's no forward, no space to move into. You'd be stuck at the boundary, unable to proceed, not because of any physical obstruction, but because motion requires space, and there is no space beyond. Another possibility is that the boundary is fuzzy, quantum in nature, that at the Planck scale, the very concept of geometry breaks down and space becomes probabilistic or discrete or simply undefined. So there's no sharp edge, but rather a gradual dissolution of the geometric structure of space as you approach the boundary. Or perhaps the edge is a place where space is still inflating, where the inflationary phase never ended, and crossing the boundary would mean entering a region of exponentially expanding space where the laws of physics are different because the inflaton field is still active, and matter from our universe can't survive there because the rapid expansion would tear apart any structures immediately. These are speculations, educated guesses based on what we know about inflation and quantum gravity and the early universe, but the truth is we don't know what the edge would be like because we've never observed it and probably never will. The edge is beyond the reach of both observation and experiment. It's a theoretical construct whose properties can only be inferred indirectly. But the important point is that the edge exists, the universe is not infinite, space has a boundary, and this fundamentally changes how we should think about the cosmos, about our place in it, about the nature of existence itself. We live in a finite bubble, one among perhaps infinitely many bubbles in the broader multiverse. And our bubble has limits, boundaries, edges beyond which nothing from our universe extends. And this should be humbling. It should make us realize that even the entire universe, vast as it is not infinite, is not unlimited, is bounded and finite like everything else we know. Now, why does this matter? Why should we care whether the universe is infinite or finite? What difference does it make to our understanding of reality or to how we live our lives? Well, the question of infinity versus finitude has profound philosophical and scientific implications. It touches on questions about mathematics and physics, about the nature of existence, about whether actual infinities can exist in the physical world or whether they're only mathematical abstractions. Infinity is a strange concept. It's not just a very large number. It's a qualitatively different kind of thing. Operations that work for finite quantities can give paradoxical results when applied to infinities. You can add or subtract or rearrange infinite sets in ways that violate our intuitions about numbers and quantities. And many physicists are deeply uncomfortable with actual physical infinities. They prefer theories where everything is finite, even if very large, because infinities tend to signal breakdowns in our theories, points where our equations give nonsensical answers, and we need new physics to understand what's really happening. Infinities show up in physics in several problematic ways. The density and temperature at the center of a black hole are predicted to be infinite, which probably means our theory of gravity breaks down there, and we need quantum gravity to describe what's really happening. The energy density of the quantum vacuum, naively calculated, gives infinity, which is clearly wrong and indicates we don't understand quantum field theory in curved space-time as well as we thought. The probability of various outcomes in eternal inflation can become infinite, making it impossible to calculate likelihoods of different observations, which is called the measure problem and is one of the biggest challenges in multiverse cosmology. So infinities are often signs of trouble, indications that we're pushing our theories beyond their valid domains, and many physicists believe that a correct final theory of physics would eliminate infinities, would show that everything in nature is finite, just very large in some cases, and if the universe itself is finite rather than infinite, that's one less infinity to worry about, one less conceptual problem to solve, and it makes physics cleaner and more manageable. Moreover, the finitude of the universe has implications for certain philosophical and theological arguments. Some arguments for God's existence appeal to infinity, suggesting that infinite regress is impossible, so there must be a first cause, or that infinity can only exist in God's nature, not in the physical world. But if the universe is finite in space and time, if it had a beginning and has boundaries, then those arguments become more pressing. The finitude of the physical demands explanation in a way that infinite existence might not. On the other hand, some atheistic worldviews are more comfortable with an infinite universe because it seems to make the universe self-sufficient, eternal, not requiring a creator or explanation beyond itself, whereas a finite universe seems more contingent, more in need of accounting for why this particular finite thing exists rather than nothing or something else. I'm not advocating for either side of that debate. I'm just pointing out that the question of whether the universe is finite or infinite has ramifications beyond physics. It connects to broader questions about existence, necessity, contingency, explanation, questions that matter to people for reasons beyond just scientific curiosity. And there's also a practical dimension. If the universe is infinite, then everything that's possible happens infinitely many times. There are infinite copies of you making every possible choice, infinite versions of Earth's history playing out every possible way, and this raises weird philosophical problems about identity and probability and decision theory. But if the universe is finite, even if very large, then your unique, your specific configuration of atoms and experiences is probably the only one, and that's both isolating, you're truly alone in a way you wouldn't be in an infinite universe, and dignifying. Your existence is special, unrepeated, mattering in a way it wouldn't if there were infinite identical copies of you. So the distinction between finite and infinite is not just technical or academic, it shapes how we understand ourselves and our significance, and getting it right matters. And based on everything we know, from cosmology, from inflation theory, from measurements of the cosmic microwave background, from theoretical considerations about the Big Bang and the nature of space, the universe is almost certainly finite, probably vastly larger than the observable region, but still finite with boundaries and edges, not extending to infinity in all directions as popular presentations often claim. We've been misled about this, perhaps unintentionally, through a combination of technical imprecision, oversimplification, and confusion between different senses of infinity and different meanings of universe. But the evidence points clearly toward finitude, and it's time we updated our popular understanding to reflect what the science actually tells us. The universe is not infinite, it has limits, it has edges, and beyond those edges there is nothing. Not empty space, but the absence of space, the end of geometry and distance and all spatial relations, the boundary of existence itself. Now, in part 2, I want to dig deeper into the observational evidence, the specific measurements and observations that support the claim that the universe is finite, because I don't want you to just take my word for it. I want to show you the actual data and reasoning that leads cosmologists to this conclusion. And I also want to address objections and alternative views, because not every cosmologist agrees that the universe is finite. There are still debates and uncertainties, and it's important to understand the full range of opinions and the reasons behind them. So let's look more carefully at the observational evidence and what it tells us about whether the universe is finite or infinite, because this isn't just theoretical speculation. We have actual measurements that constrain the possibilities and point toward specific conclusions. The most important observations come from the cosmic microwave background, the CMB, which is the oldest light in the universe, radiation that was emitted when the universe was about 380,000 years old and has been traveling through space ever since, reaching us now from all directions as a faint microwave glow. The CMB has been mapped with extraordinary precision by satellite missions, first COB in the 1990s, then WMAP in the 2000s, and most recently Planck, which operated from 2009 to 2013 and gave us the most detailed picture of the early universe we've ever had. And these observations tell us an enormous amount about the universe's properties, its age, its composition, the density of matter and dark energy, the rate of expansion, and crucially for our purposes, the geometry and topology of space. The key measurement is the power spectrum of temperature fluctuations in the CMB, which tells us how the temperature varies across the sky on different angular scales, how much hotter or colder one patch is compared to another patch separated by a certain angle. These temperature fluctuations, which are only about 1 part in 100,000, reflect density variations in the early universe, regions that were slightly denser or less dense than average, and these density variations are what eventually grew through gravitational collapse to form galaxies and large-scale structure. The pattern of fluctuations is determined by the physics of the early universe, by how sound waves propagated through the hot plasma before the CMB was emitted, and this pattern depends sensitively on the geometry of space. If space is positively curved like a sphere, the pattern looks one way, peaks at certain angles. If space is negatively curved like a saddle, the pattern looks different, peaks at other angles. And if space is flat, the pattern has a specific signature that distinguishes it from curved geometries. The measurements show that space is very nearly flat. The curvature parameter omega k is measured to be negative 0.0004 plus or minus 0.0004, which is consistent with 0, with perfect flatness within the measurement uncertainties. Now, this doesn't immediately tell us whether the universe is finite or infinite, because as I mentioned earlier, flat space can be either infinite or finite depending on the topology, whether space wraps around on itself or extends forever. An infinite flat space is topologically simple. It's what mathematicians call Euclidean 3 space, just extending to infinity in all 3 directions. But finite flat spaces have more complicated topologies. They involve identifications where you wrap the space around, gluing opposite edges together in various ways, and there are actually infinitely many different ways you could do this. Infinitely many different flat topologies, each corresponding to a different way the universe could be finite while remaining geometrically flat. The simplest examples are the 3 torus, which is flat 3-dimensional space with all 3 directions wrapping around like a 3-dimensional version of a donut, and the Poincaré dodecahedral space, which has a more complicated structure involving 12-fold symmetry and specific identifications of faces of a dodecahedron in a higher dimensional sense. These are just two examples among infinitely many possibilities, and each would give slightly different signatures in cosmological observations if the wrapping scale is small enough that we can detect it. The way to detect topology is to look for correlated patterns in the CMB. If the universe wraps around, then light from a single region reaches us from multiple directions. We see the same physical structures from different angles, and this should create matching circles or correlated temperature patterns in the CMB map. Researchers have searched extensively for these signatures, looking for matched circles measuring correlations in temperature fluctuations that would indicate we're seeing the same structures repeated in different directions due to wrapping, and the results are inconclusive. No definitive topology signature has been found, which means either the universe is infinite or it's finite, but the wrapping scale is larger than the observable universe, so we can't detect it yet, or the topology is such that its signature is too subtle to detect with current measurement precision. The absence of detected topology doesn't prove the universe is infinite. It just means we haven't found evidence for finite topology within the observable region. And given that the observable region is a tiny fraction of the total universe, if inflation occurred as we think it did, it's entirely possible that the universe is finite with a wrapping scale far beyond what we can currently observe. In fact, theoretical considerations from inflation strongly suggest this is the case, because inflation naturally produces a universe much larger than the observable region, potentially hundreds or thousands or more times larger. And if the universe has finite topology with wrapping at those scales, we wouldn't see it in current CMB observations. We'd need to wait until the observable region expands through further cosmic evolution, or we'd need much more sensitive measurements to detect the incredibly subtle correlations that would indicate wrapping at such large scales. So the observational situation is this. We know space is very close to flat. We haven't detected signatures of finite topology, but we also haven't ruled it out, especially for topologies with large wrapping scales. And the theoretical considerations from inflation suggest the universe is finite, but much larger than the observable region, which would explain why we don't see topology signatures yet. Now, there's another line of observational evidence that's relevant, which comes from the statistics of temperature fluctuations in the CMB on the very largest scales, angles spanning significant fractions of the entire sky. These large-scale fluctuations are interesting because they reflect physics from the very earliest moments, the initial quantum fluctuations during inflation that seeded all structure, and they're sensitive to global properties of the universe, like its total size and topology. If the universe is finite and not too much larger than the observable region, say only 10 or 100 times larger, then we should see a suppression of power on the largest scales, fewer and weaker temperature fluctuations at large angles, because fluctuations larger than the universe itself can't exist. The longest wavelengths are cut off by the finite size. And interestingly, observations do show something called the large-scale anomaly, a deficit of power at large angular scales compared to what standard models predict for an infinite universe. The quadrupole and octupole moments, which represent the largest scale fluctuation patterns, are lower than expected, suggesting that maybe the universe is cutting off these long wavelengths. Now, this is not definitive evidence because the statistical significance is marginal. We're looking at only a few independent measurements of these large scales because we only have one sky to observe. So random fluctuations could produce this pattern by chance, but it's suggestive. It's consistent with a finite universe that's maybe 100 or a few hundred times larger than the observable region, which would naturally suppress the largest scale fluctuations. Some cosmologists take this seriously as tentative evidence for finite topology, while others are more skeptical and think the anomaly will go away with better data or better understanding of systematic effects in the measurements. So the observational picture is ambiguous, but leans toward finitude. We have flat geometry, which is consistent with either infinite or finite topology. We have no detected topology signatures, which could mean either infinite universe or finite universe with large wrapping scale. And we have suggestive hints of large-scale power suppression, which is consistent with a finite universe but not definitively proven. Combining this with the theoretical arguments from inflation, which strongly favor a finite universe much larger than the observable region, the most reasonable conclusion is that the universe is probably finite, probably enormous, but bounded, probably with an edge far beyond the cosmic horizon where space ends and nothing exists beyond. This is the mainstream view among cosmologists who work on these questions, though there's still uncertainty and debate, and alternative views are definitely possible. Let me now address some of those alternative views and objections, because it's important to understand the full landscape of opinions and not pretend there's more consensus than actually exists. One alternative view is that the universe is truly infinite, that the Big Bang created an infinite amount of space all at once, that inflation operated on an already infinite space and just smoothed it out and made it uniform, and that there's no edge, no boundary, space extends forever in all directions. Proponents of this view argue that there's no fundamental reason to prefer finite over infinite, that both are mathematically consistent with general relativity and with observations, and that in the absence of definitive observational evidence for finite topology, we should remain agnostic. They point out that the theoretical arguments for finitude, while suggestive, are not conclusive, that inflation could work with either finite or infinite initial conditions, and that our discomfort with actual infinities is more philosophical than scientific, a preference rather than a requirement. And this is a fair point. There's no knockdown proof that the universe must be finite. The evidence is suggestive but not conclusive, and people with different prior beliefs about infinity and different assessments of which theoretical considerations are most important can reasonably come to different conclusions. My own view, and the view of many cosmologists I respect, is that finite is more likely based on the totality of evidence and theoretical considerations, but I acknowledge that infinite remains possible. Another alternative view, one that's perhaps less common but still taken seriously by some researchers, is that the universe is not just finite or infinite in the conventional sense, but has a more exotic structure, perhaps fractal or multiply, connected in complicated ways, perhaps with a boundary that's not a simple edge, but something more subtle and interesting. For instance, some models suggest the universe could be a three-dimensional manifold embedded in a higher dimensional space with a boundary that's a two-dimensional surface in three space, but a three-dimensional structure in the higher dimensional embedding space, and this boundary could have interesting physics. Maybe it's where our universe interfaces with other universes, or with the bulk space of string theory, or with whatever exists beyond. These are highly speculative ideas, not mainstream, but they remind us that we shouldn't be too confident in any particular picture. The universe could surprise us, could have a structure we haven't imagined yet. And there's also the view, which I've been advocating, that we need to distinguish between the universe and the multiverse, between our bubble and the totality of all bubbles in eternal inflation. In this view, which is increasingly standard among cosmologists who accept inflation and take its predictions seriously, the universe, meaning our bubble, is finite, but the multiverse is infinite. There are infinitely many bubbles forming continually through eternal inflation. And the totality of this multiverse generating process extends to infinity in both space and time. So in one sense, there is infinity, but it's not the infinity of our universe extending forever. It's the infinity of many universes, each finite, collectively forming an infinite ensemble. And this distinction matters because when people ask whether the universe is infinite, they usually mean, is our universe infinite, the space we inhabit and could potentially explore? And the answer to that is almost certainly no. Our universe is finite. The multiverse might be infinite, but that's a different claim. It's about the totality of all causally disconnected regions, not about the extent of the space we're part of. So depending on how you frame the question, you can get different answers, and clarity about what we're asking is essential to avoid confusion. Now, I want to address one more important question, which is what it would mean observationally if we discovered definitive evidence that the universe is finite with a specific size and topology. How would that change cosmology and physics more broadly? If we detected a clear topology signature in the CMB, matching circles or correlated patterns that definitively showed space wraps around at a certain scale, that would be revolutionary. It would tell us the precise size of the universe, allow us to map its global structure, and would have profound implications for theories of the early universe and inflation. It would tell us how much inflation occurred, how long the inflationary phase lasted, what the initial conditions were. And these are currently open questions where we have theoretical models but not definitive answers. Knowing the size and topology would also affect calculations of probabilities in the multiverse, because finite universes have finite volumes and finite numbers of possible configurations of matter, which makes probability calculations more tractable than in infinite universes where you have to deal with infinite numbers and measure problems. And it would affect our understanding of the multiverse itself, because if our universe is finite with a specific size, that tells us something about the landscape of possible universes, about what parameters control the size of inflating regions, about how bubble nucleation works in eternal inflation. So detecting finite topology would be a major discovery with ramifications throughout cosmology and fundamental physics. Unfortunately, given the current evidence and the likelihood that any finite topology has a wrapping scale much larger than the observable universe, we probably won't detect it anytime soon. We'd need dramatic improvements in observational capabilities, or we'd need to wait billions of years for the observable region to expand enough to potentially see repeating patterns if they exist. But the question remains open, and future observations might surprise us, might reveal structure we don't expect, and that's part of what makes cosmology exciting. We're probing questions about the ultimate nature of space and existence using observations of the real universe, not just theoretical speculation. Now, let me shift to a slightly different angle, which is what the finitude of the universe means for the far future. Because if the universe is finite rather than infinite, that has implications for the long-term fate of matter and energy and structure. In an infinite universe, every possible configuration of matter occurs infinitely many times. There are infinite copies of you, infinite Earths, infinite galaxies, and this infinity continues forever into the future as well as existing in the present. But in a finite universe, even a very large one, there are only finitely many particles, finitely many possible states, and over extremely long times, the universe cycles through these states, eventually exhausting possibilities and potentially reaching a kind of end state where nothing new can happen. This is related to the Poincaré recurrence theorem, which says that in a finite system, if you wait long enough, the system will eventually return to a state arbitrarily close to its initial state and will cycle through all its possible states infinitely many times over infinite time. Now, this requires some assumptions, like the universe being a closed system with a finite phase space, and it's unclear whether these assumptions hold in cosmology, given cosmic expansion and increasing entropy. But the basic intuition is sound. In a finite universe, there are only so many ways things can be arranged, and if time is infinite, then configurations must repeat, whereas in an infinite universe, you never run out of new possibilities. You never exhaust the range of structures and patterns because there's always more space to explore, more matter to arrange in new ways. So finiteness constrains what can happen over cosmic time in ways that infinity doesn't. And this might be relevant to questions about the ultimate fate of consciousness and information in the universe. If the universe is finite and time is infinite, do we get eternal recurrence, the same configurations appearing again and again? Or does entropy increase irreversibly, driving the universe toward heat death where nothing interesting happens anymore and recurrence becomes impossible? These are deep questions that connect cosmology to thermodynamics and statistical mechanics, and the answers depend on details of physics we don't fully understand, particularly the long-term behavior of dark energy and whether the accelerating expansion continues forever or eventually reverses or transitions to some other phase. But the finitude of the universe matters for these questions. It's a boundary condition that constrains possibilities and affects what we should expect in the far future. Now, I want to come back to the central claim and make sure it's crystal clear, because I've covered a lot of ground and I don't want the main point to get lost. The claim is this: the universe, meaning the region of space that originated from our Big Bang, that contains all the matter and energy that's causally connected to us or ever will be, is almost certainly finite, not infinite. It's vastly larger than the observable region, probably hundreds or thousands or more times larger, but still finite, with an actual boundary beyond which space ends. The evidence for this comes from inflation theory, which naturally produces finite bubbles, from the flat geometry of space, which is consistent with finite topology, from the absence of observed topology signatures, which suggests wrapping at scales larger than observable, from large-scale anomalies in the CMB, which hint at finite size effects, and from theoretical considerations about the Big Bang and the avoidance of actual infinities in physics. This is not certain, not proven beyond all doubt, but it's the most likely scenario based on current understanding, and it's what most cosmologists believe when they think carefully about the question, even if popular presentations often claim the universe is infinite without acknowledging the evidence and reasoning that suggests otherwise. And this matters, not just because we should be accurate about what we know and don't know, but because the finitude of the universe changes how we understand our place in reality, affects questions about meaning and uniqueness and the far future, and corrects a widespread misconception about one of the most fundamental properties of the cosmos. The universe is not infinite. It has boundaries. It has edges. And beyond those edges there is nothing. Not space, not matter, not even emptiness in the usual sense, just the end of spatial existence. And in the final part, I want to explore what this means philosophically and existentially, how the finitude of the universe should shape our understanding of ourselves and our significance, and what it tells us about the nature of reality and existence. Because these aren't just abstract cosmological facts. They touch on questions of meaning and purpose and how we should live, and understanding the structure of the universe, its size and shape and boundaries, is part of understanding ourselves and our place in the grand scheme of things. So let's go deeper into the implications and see what the finitude of the universe means for us as conscious beings trying to make sense of this strange reality we inhabit. So let's think about what it really means, to live in a finite universe rather than an infinite one, because this distinction has profound implications for how we understand ourselves, our significance, the uniqueness of our experiences, and what we can hope for in both the near and distant future. When people first encounter the idea that the universe might be infinite, there's often a sense of vertigo, of being overwhelmed by the scale, of feeling insignificant in the face of endless space extending forever in all directions. But there's also a strange comfort in it, because if the universe is truly infinite, then everything that's possible happens somewhere. Every version of you exists. Every choice you could have made was made by some copy of you. Every story that could be told is being lived somewhere in the vast expanse of infinite space. You're never truly alone, never truly unique. Your existence is repeated infinitely many times throughout the cosmos. And in some sense, that makes individual failures and tragedies less absolute, because somewhere else it all worked out differently. Somewhere your lost loved ones are still alive. Somewhere you made better choices. Somewhere humanity thrived instead of struggled. But if the universe is finite, all of that goes away. You are unique. The specific arrangement of atoms and experiences that constitutes your existence occurs exactly once. Nowhere else in our universe is there another you. And when you die, that unique configuration is lost forever. No copies remain. No alternative versions continue in other regions. Your choices matter in a way they wouldn't in an infinite universe, because the outcomes of your decisions are not replicated elsewhere. What you do actually makes a difference to the total state of reality, rather than being just one instance among infinite instances. And tragedies are truly tragic. Deaths are truly final. Lost opportunities are genuinely lost, not just for you personally, but cosmically, because that specific possibility will never be realized again anywhere in our finite bubble. So finitude makes existence heavier, more consequential, more precious, because it's singular and unrepeatable, but also more isolating, more final, more filled with genuine loss, rather than just local manifestations of patterns that exist elsewhere. And I think this is actually a more honest, more mature way to understand our situation than the infinite universe picture. Because even if the universe were infinite, those other versions of you are causally disconnected. They might as well not exist from your perspective. You'll never meet them or interact with them or be comforted by their existence. They're not you in any meaningful sense. They're separate beings with separate experiences. And your own death is just as final for you whether or not copies exist elsewhere. So the psychological comfort that infinity might provide is largely illusory, based on confusion about identity and causation. And acknowledging finitude forces us to confront the real nature of our existence, the genuine stakes of our choices, the actual weight of consciousness and experience in a universe that generates them rarely and temporarily. Moreover, finitude